mentored several PhD scholars and has spearheaded advanced research projects in collaboration with international institutions in Slovenia and Sri Lanka. He is also a senior member of IEEE and a life member of ISTE and the System Society of India. His scholarly contributions include over 115 international journal publications, numerous patents, including innovations in inverter technologies, and authorship of renowned textbooks in the field. A recipient of many prestigious awards, including the Best Teacher Award from the Government of Telangana and the Engineer of the Award by IEI, Professor Satish Kumar Sir has also represented India globally through keynote speeches and collaborations in USA, Japan, Switzerland, Paris, and many more. We are truly privileged to have such an eminent personality amongst us today.
Thank you. Thank you. Pointer. Okay, good afternoon everyone. So first of all, I thank Dr. Amrendra and also Honorable Vice Chancellor for providing an opportunity to deliver a lecture on the power electronic converters. Because the role of advanced digital controllers in power electronic converter applications. In the power electronic converter applications, the inverter is also plays a major role. So what is that? The inverter, that may be a two-level inverter or otherwise multi-level inverters. So the inverter operation by using the pulse width modulation techniques, we are very much aware of that. So in an inverter, we are giving a DC supply and we are achieving AC supply. In different levels, we are going to operate the switches which are present in the inverter. In a different sequence, we are going to operate to get the desired output voltage. So desired output voltage is AC voltage, actually alternating voltage in fact. But no inverter will give the pure sinusoidal output voltage. So all the inverters will give quasi square wave output voltage only as well. So for example, some particular applications demands pure sinusoidal voltage only, or otherwise an alternating voltage with less total harmonic distribution. The normal inverter cannot be utilized for that applications. So for example, your application demands a pure sinusoidal wave, or otherwise your application demands a sinusoidal voltage waveform which is having very low total harmonic distribution. In such cases, normal quasi square waveform output inverter is not enough for such applications. So that's why how to operate the inverter will be decided by the pulse width modulation techniques. So in the pulse width modulation techniques, the latest trend is nowadays we are going to use space vector pulse width modulation techniques. So I want to enlighten a focus on space vector pulse width modulation technique as well as a basic simple inverters, which how we are going to operate them. Okay. So here coming for this, the contents are pulse width modulation and basic two-level inverter, multi-level inverter, and use space vector pulse width modulation method for diode point clamp to multi-level inverter. There is nothing but neutral point clamp to multi-level inverter. So what the contents is, what is meant by pulse width modulation? We are very much aware of that. What's the purpose of the pulse width modulation? For example, in an inverter, we are having 6 switches, 1, 2, 3, 4, 5, 6. In each lane we are having 2 switches, and we are giving the DC supply. And at the midpoint of that, we are trapping the AC voltage. So that AC voltage, as we are giving the DC, we are going to get the AC voltage like quasi square waveform output. When it is not sinusoidal, we are saying it is alternating some positive value, say negative value, positive value, negative value. That's why we are claiming that is nothing but alternating voltage, but it is not an AC. So, but when do we turn on the thyristor or otherwise MOSFET, which is present in the IGBT, which is present in the inverter, will be decided by the pulse width modulation technique. Just like that, I want to operate for 30 degrees, 70 degrees, 90 degrees, like that randomly also we are able to get the output voltage. But that output voltage will give the inferior performance. That is, but it will have lot of total harmonic distribution. That's why when to turn on your switch, which switch you have to turn on, up to what time period you have to turn on, that will give the the voltage which is near to the sinusoidal. So that's why what is the basic method normally we are going to use. What is the pulse width modulation? So we are going to control the fundamental component of the output voltage. For example, you want to get various fundamental component of the output voltage, that will be decided by using the pulse width modulation technique. And also to achieve good spectral performance, the lower achieve good DC pulse relation. We are giving the DC to the inverter using space vector pulse width modulation technique. It is 50% more compared to the normal sinusoidal pulse width modulation technique. That's why 1. So these are the requirements of why pulse width modulation technique is used. So this is a basic only, but definitely there is no doubt you will get some idea about the basic things. How to, what is the inverter, what's the multi-level inverter, and how to implement that also we are going to discuss. So here the basic pulse width modulation techniques are, one is a single pulse width modulation, only one single pulse we are going to do, and multiple pulse width modulations, sinusoidal pulse width modulation. These all are conventional pulse width modulations. And apart from that, some advanced pulse width modulation techniques are trapezoidal modulation, radial modulation, stepped modulation, delta modulation, and finally space vector pulse width modulation technique. So what are these techniques we are going to see? For example, if we have single pulse width modulation technique, what we are using, this is a carrier pulse and this is the reference. Wherever the carrier reference value is greater than this carrier pulse, during that interval we are providing a pulse to a transistor switch. Okay, so that in one cycle we are going to have only positive and negative. So that what is the output voltage? We are going to get a continuous output voltage from alpha 1 to alpha 2 to the positive step, and continuous during 5 plus alpha 1 to 5 plus alpha 2 we are going to get the negative pulse. So this is our single pulse. So that we are able to get one pulse is given only one voltage waveform we are going to get positive and negative. That is our single pulse. Instead of that, if the carrier frequency is more, multiple number of pulses like this. This is a carrier signal. This carrier signal and this is the reference signal. They are giving more. Wherever the reference signal magnitude is greater than the carrier signal, during this instant we are providing a pulse, and there is no pulse, pulse, no pulse, pulse, no pulse like that. So that what is the output voltage we got? This is the output voltage. But this output voltage also, if we find out, if we analyze, harmonically analyze, the THD will be about 90% or 80% like that. So a output voltage waveform of a inverter is inferior, which is possessing near about 80 or 70% of the total non-ratio share. How can you expect the best results when it is applied for a particular specific applications? Right? For example, lighting purpose, okay, no problem. We have the battery, we have an inverter, we are getting positive, negative. It is not sinusoidal. Even though that our steering fan or otherwise our tube lights and everything will be on. There's no, we need not bother about it. But whenever we are doing for a process control, the ultimate the THD should be very less. And also when we are using the multi-level inverter, instead of one voltage waveform, we are going to get the waveform in terms of the steps. So that steps are near the fundamental component, if you see, that is near the effect of the sinusoidal waveform. So that's why whatever is here, this is multiple pulse width, this is sinusoidal pulse width. Normally we are going to use the sinusoidal pulse width modulation techniques. And also for coming for the hardware implementation, the most of the cases we are using only 2-level inverter only. All inverters, what we are getting in the market, in Indian market, we are only getting 2-level inverter. But coming for the 3-level or 5-level or 7-level, that is under, still those are under what's that research areas only, and some small prototypes only they are able to produce. Okay. So here we are using here, this is the carrier signal, and our intention is we want to get sinusoidal. So that's why what we are using here, we are using a carrier signal and we are comparing wherever the carrier signal is, this fundamental difference waveform is greater, during that instant we are doing. If you see the pulses here, the pulses are not uniform. Because sinusoidal, we are comparing with the sinusoidal, somewhere it is magnet, the length is more and length is less like that. So this is giving a good results. If you see that output voltage, we are going to get the output voltage like this. Positive side and this side we are going to get. When the spectrum is having so many pulses in the form of the pulses, the spectrum performance is improved. So that's why normally we are going to use sinusoidal pulse width modulation. So when to start, when to stop, when to give a pulse, provide a pulse to a switch, and when to withdraw a pulse is also most important. So for that purpose we are using this. We are deciding by comparing a what is a carrier waveform with the reference voltage waveform. But coming for the, this is trapezoidal, like a trapezoidal carrier reference waveform we are going to take. And this is like a staircase, they are compared with the triangular. and wherever that is greater, magnitude is greater, we are holding a pulses like that. This is step in terms of step we are going to take. These are various advanced. This is the delta, this is strand we are going to take, and final one is space vector pulse width. We are going to focus on this. So what is a space vector pulse width modulation is? It is based on a vector rotating in a space. For example, if we give a three-phase AC supply, what is the basic advantage of this three-phase AC supply apart from generation as well as transmission? Application point of view. What is the basic beauty of the three-phase AC supply? Application point of view. There is no three-phase AC supply, there is no three-phase induction motor. Because when a three-phase voltage is provided to the stator winding of the induction motor, we are going to get rotating magnetic flux. If there is no rotating magnetic flux, there is no high horsepower, high HP motor, high kilowatt motors. Only we are dependent on only fractional kilowatt motors only. Okay. So in the three-phase induction motor, if we can visualize, if we give a three-phase AC supply, we are getting three voltage waveforms, 120 degree displacement. For every 60 degrees, third one is absent, only second is dominating, and one is positive, the other one is second, negative. So that how we are getting, we are going to get a vector for every 60 degrees it is jumping. For every 60 degrees, if we take the resultant vector is 60 degrees, 120 degrees, 180 degrees, like that we are going to get. When a three-phase AC supply is given to a stator of the induction motor, it is giving a rotating magnetic wave or a space vector which is rotating with some speed, synchronous speed, which is rotating with a synchronous speed. In that similar way, if an inverter switches are provided with some sort of pulses, some sequence of the pulses, if it is able to develop a vector rotating in nature, that means that your inverter is fast. How it is fast? It is able to give a output voltage which is equivalent to three phase. When three-phase supply is given, rotating magnetic field is there, right? Fine. I have an inverter, I have given a DC supply, I have given some pulses. So what happens? The resultant voltage of this inverter, if it is provided a vector jumping for 60 years, that indicates that your inverter is giving a qualified AC output voltage. It is an equivalent qualified AC output voltage. That is a meaning behind this space vector pulse. Based on that, it was developed. So what is the outcome is required here? Your inverter should be turned on in such a way that overall output A0, B0, C0, all four voltage output will gives a vector which is rotating in nature. If it gives a vector rotating in nature, your inverter is fast. So how do we make our inverter to develop a vector rotating in nature is the question. That is called space vector pulse propagation. Clear? How we are using as space vector pulse propagation, we will see. Clear? Point is clear? If your inverter is able to produce, so that you have to operate your inverter such that it will give a rotating vector. When your inverter is producing a rotating vector, your inverter is giving a three-phase equivalent sinusoidal output voltage. How do we operate our switches to get that? That is the question. How do you operate our inverter to get that a rotating vector? That is the question. So for that purpose, we are going to depending on space vector pulse propagation. I will tell you how we are going to get it. It will give the advantage of better spectral performance compared with sinusoidal pulse propagation and enhance the DC pulse relation. It is 50% more DC pulse relation will be there, and it will generate less harmonic distortion in the output voltage or currents in comparison with sinusoidal pulse propagation techniques. Okay, so these are the advantages with this. So what is the principle of space vector? Principle of space vector means we have a two-level inverter where pole voltages are VA0, PV0, VC0. If they are resultant, VA0 resultant, PV0 and VC0 collect to 3, 4 voltage resultant has to give a rotating vector. So that reference vector is nothing but first voltage VA0 plus second pole voltage PV0 e to the power of j2 by 3 plus the third voltage VC0 e to the power of minus j2 by 3. So that if they satisfy a rotating vector, then you achieve your requirement. Then your output as the inverter is similar or equivalent to a sinusoidal three-phase supply voltage. Right? So in that way we are going to think of that. So it reads the sinusoidal voltage. How do we implement that? It reads the sinusoidal voltage as a constant amplitude vector rotating at a constant frequency. So it will have V reference magnitude. It is a constant vector which is rotating with a constant vector. How it is rotating? It is jumping for every 60 degrees or every 30 degrees or every 50 degrees or every 7.5 degrees. That depends on how we are operating our switches. Okay. If jump for every 7.5 degrees, what is the meaning? Instead of 60 degrees, it is jumping for every 7.5. Means it is smooth vector. When the vector rotation is very smooth, instead of jumping, very smooth, and we can control this magnitude is also. So then your inverter output voltage is superior or it is similar to your sinusoidal effect. So that we are going to use here. So VWA technique approximates the reference voltage by a combination of 8 switching states. Okay, చూస్తారా sir? Okay, it will treat as it is a combination of 8 switching states. So what are the 8 switching states? One is 1, 0, 0, 0, 1, 0. Like that we are going to have various switching states. Okay, just I will show you. Okay, any doubts or